So what is the analogy? The analogy is dates. Okay, so suppose that I have 3 dates that I want to communicate to my friend. So the dates are just going to be a birthday, the date of the first CS161 lecture, and the day of the CS161 final exam. And the challenge here is that to communicate these dates, you have to only write down 9 2-digit numbers. So you can't have any slashes, no dashes, no commas, nothing like that. And so one sequence of numbers you can try is you can try writing the year, month, day of the first date, then the year, month, day of the second one, then the year, month, day of the third one. And so that's what we've done here, right? The year is 99, the month is 11, and then the day is 02. And the second one, the year is 2020, so 20, the month is June, so 06, and then the day is 22, and so on. Or you can try doing this backwards and you can have day, month, year within each date. So the first one, right, the day is 02, and the month is November, which is 11, and then the year is 1999, which is 99. And you do this for all 3 dates. So here we have 2 sequences of 9 numbers. Each one encodes those 3 dates. And the question is, does it really matter which one I use? It doesn't really matter, right? Both of them encode the same dates. The important thing is that my friend and I have coordinated and we know which one of these we're using. So what does all this have to do with the memory? Well, the memory is the exact same thing. So the first one, the year, month, day version, we call this big endian. And the reason we call it that is because we start with the biggest unit, which is the year. And then the second version where we have day, month, year is going to be called the little endian version. And this is because we start with the smallest unit, which is the day. And again, in both of these versions, any group of 3 numbers is a date. And the only difference is, do I read them forwards or do I read them backwards? So now let's go back to how we form words. And it turns out that forming words is exactly the same, right? We have this group of 4 numbers, and I need to somehow combine these 4 numbers to form a word. And the question is, do I read these numbers forwards or do I read these numbers backwards? Well, the x86 designers decided to make x86 little-endian, so that means that we should read the word backwards. So that means that if I want to form a word out of these 4 bytes, the word that comes out is actually 44332211. Again, just like the dates, every group of 4 bytes is a word, and the difference is just how we're reading it. And the agreed upon reading between the x86 creators and us is that it's going to be backwards, little-endian. So let's go back to the dates for just a second, and let's look at the little-endian sequence. So this is the day, month, year sequence. Now, if I ask you for the first date in this sequence, you would take the first 3 numbers and you would read them off and you would tell me it's November 2nd, 1999, because you know that the first number is the day, the second number is the month, and the third month is the year. Now, I can also ask you for the first number in the sequence, and you can just take a look at this. You can ignore dates and just think of this as a regular sequence, and you would tell me the first number is 2 because you just look at the first number and it's a 2. So again, what does this have to do with memory at all? It's the same thing with little-endian words. So I can ask you to read off the entire word, and so that means you would have to take the 4 bytes at the address, right? So in this case, the address 0, I would have to take all 4 bytes and then read them backwards. So give you 44332211 as the word. But I can also ask you, what is the byte at this address? And then you would just read off the very first byte there, and that's 11. So usually in 161, or in x86 in general, every row or every word, right, is just going to be treated as a whole word. It's very rare that we actually have to deal with individual bytes. So generally, you're not going to see anything written this way. You're going to see every row just have the word. So you're just going to say 0x44332211. It'll just be written like that. But remember that under the hood, what it actually looks like is that the first byte is the 11, the second byte is the 22, the next byte is the 33, and the last byte is the 44. So remember that under the hood, the word is kind of being stored in backwards order, but then when we write it out, sometimes we just write out the word because we don't want to have to keep thinking about forwards, backwards, forwards, backwards. And in project 1, if you ever want to write a word into memory, you have to write it backwards. So let's say I want to write the word 44332211 into memory. I need to reverse that into 11223344 and then enter that into memory. So this is probably going to sound very confusing if you haven't encountered it before. Don't worry, I would say this is probably one of the trickiest parts of the entire unit. The homework, the projects are going to remind you of this endlessly, and you'll get lots of practice and be very familiar with it by the end, trust me. So don't worry if you don't have this right away, but do keep in mind that the word and the bytes are kind of like opposites of each other. They're read in different directions. One final note here is you might remember from 61C there are these things called registers, and a lot of the operations in RISC-V use these registers. So like add A0, A0, T1, stuff like that. So the question is, on this diagram, where are the registers located? So maybe take a second and see if you remember where they are. And the answer is they are not on this diagram. Sorry, is this your question? This diagram shows all the memory in RAM. So all this memory that's laid out is located in RAM. And the registers are actually located on the CPU. And the registers are there because if you put them directly on the CPU, it's very, very fast to access them. And this memory is going to be a lot slower to access. So the registers are, there's much fewer of them. So they're usually just referred to by names and not by any addresses. So remember, registers do not have 32-bit addresses. They usually just have names, and they're not located anywhere on this diagram. They're kind of located off to the side on the CPU.